All right, welcome back to the Java EE programming course, and this is lecture number 6, and this one is going to be on probably just going to cover transaction management today. It's about 85 slides long, and we're not going to get that far through it, but half of it's about transaction management, and it goes into JSP as a concept. So JSP is our next big programming thing, and the concept of the JSP is actually it's not really tied with transaction management, but the concept of transaction management is core to what we're doing with distributed applications. So that's why it's sort of in here for today. So what we're going to talk about is basic concepts related to transaction management and web tiering as well. We've seen a little bit of web tiering already. When we get into JSP, we're going to see a lot of web tiering information in terms of servlets. Because web tiering is done to create the servlet environment. We have JSP pages, which is, if you're not familiar with JSP, it's kind of like ASP, but if you're not familiar with ASP, you have no idea what I just said either. Sort of like a scripting language that's a compiled language. So it's, instead of using JavaScript and scripting in a page with HTML, you're writing Java code in a page with HTML. And then the page, the JSP page, gets compiled on the server before it's run. So it gets created, the application itself is sort of created in real time, which allows for a lot more flexibility in terms of the application design and the application editing, and especially for the presentation of the material. And so JSP is used a lot when you're primarily interested in the user interface and the user interaction, so you can get content, dynamic created content to appear on a website. And so it's sort of the website slash scripting tool slash compiled language that's used with servlets. So it goes, the JSP pages go into a servlet environment and then they get compiled and run. So that's really probably not going to be talking about that though until next week in terms of the lecture. Unless I get through transaction management at the speed of light, which I might do. So transaction management and transactions themselves, we actually have a Java transaction library or API called the JTA, Java Transaction API, which is used for Java transactions. And so the concept of a transaction is kind of important when it comes to application development. And most people are wondering, well, what in the world are you talking about? Why are we talking about transactions? It's basically a concept that comes from databases. When we think about databases, we always think of, if you're going to use an ATM machine as an example, and the customer is going to go up to the ATM machine and they're going to withdraw money, and then the power goes out somewhere halfway in the middle of their transaction. They've put their card in, they've authenticated themselves with a password, they've selected the account, they selected withdrawal, and then it said, okay, now dispensing your money, and then the power goes out on the machine. Wouldn't it be nice if the transaction rolled back after it detected an error and said, well, the customer didn't get their money, so let's take and reverse the transaction, reverse the task that withdrew it from the account and put it back. Well, that's what transaction management is supposed to be doing. So you don't have to go into the bank and say, hey, I was asked for my $20, but it didn't come out. And then, you have to worry about, well, now everything's out of sync. We're going to give you the $20, but, now we have to manually update your account, and it gets all screwy. So in terms of transactions, by definition, it's a group of processes that either all succeed or they all fail. If they all succeed, we commit. If they all fail, we roll back. And the concept of all is kind of interesting as well. Not necessarily all of them have to succeed or all of them have to fail. But if we have one failure, then we don't really have a transaction. It's not really a complete set. So it is sort of an all or nothing. In terms of transaction management, that's the mechanisms for specifying the development of a distributed multi-tier enterprise application. Yada yada. It's keeping track of all of the different pieces of the application. So we get a management or transaction manager object, and the object is responsible for doing the checks on each one of the different objects, instances that are created, so that we can see if one of them failed, if one of them didn't fail, and what was going on essentially. So standard services that are offered through the J2EE is that JTA, as I mentioned a few minutes ago. the Java Transaction API. And you create instances of transaction objects, and you tell the objects to listen to certain behaviors from certain method invocations. And if everything is successful, then the management object says, okay, it's a good transaction, let's commit it. If not, then the object comes back and says, nope, failure, we have a failure, so roll it back. Don't commit the changes. So by enforcing strict rules, the application's ability to access, update data, do transaction management, ensures data integrity, ensures consistency, ensures an adequately running program. It means that the transaction manager ensures that the unit of work either fully completes or has no effect at all in terms of the outcome. So it frees the programmer from dealing with complex issues of data access, synchronizing failures, failure recovery, and multi-user programming, essentially. So an example would be the ATM for a bank, as I mentioned a few minutes ago. In fact, ATM transactions are kind of important that they work correctly. Otherwise, you're going to end up with accounts that have the wrong balance in them. And even if the account's off by a penny, if you have 1 million accounts that are off by a penny, that can add up to a lot of money eventually. So here's the concept of the ATM. And the ATM is the machine that's riding between the customer and the bank. We've all used ATMs. Hopefully we know what these things are. We enter a card. We enter a PIN. We verify the card and the PIN. Then at the ATM does this verification. It goes to the bank to verify this information. The authentication information comes back to the ATM. The ATM says, okay, let's start the transaction. Let's make this start working. And then the customer might select a withdrawal, select an account, select an amount, and then if an error occurs before you actually perform the withdrawal, in the example I gave you, nothing's wrong. I mean, we don't really care until we hit withdrawal from my account. If your money doesn't pop out, you're gonna have an issue essentially. Well, you're going to be disappointed because you're not going to have the 20 bucks or 40 bucks or however much you tried to withdraw. So there's no problem up to this point. So there's no rollback. There's nothing really needs to be done. But once a change starts occurring to the data, then if there's a problem when it performs the withdrawal, if it doesn't get a confirmation back that says the withdrawal was completed successfully, what happens if the network goes down here? Well, we've got issues. And that's where transaction management is going to save our application or save our customers' opinion of our company, essentially. It's supposed to dispense the cash. If it doesn't dispense the cash, we have to be able to, tell that this happened. This is not error checking. It's not debugging. It's not anything having to do with the application. It's the fully functional application that in a perfect world would run perfectly, put in a non-perfect environment. And when you put it in a non-perfect environment, you've got network failures, you've got machines that go down, hardware failures, software incompatibilities, viruses, all sorts of different stuff that happens with computer equipment. And, it's the transaction management part of it is making sure that the transaction itself, in the best of all worlds, happens correctly. So there's this thing called the acid test. Have you guys heard of this? It's a way of judging the quality, essentially, in the way of designing. It's kind of like a design method for designing applications. So the mnemonic is ACID to remember these characteristics. And these characteristics are things that the transaction management is taking care of for you. It's qualities in the software that the transaction management is going to make sure that we have these particular characteristics. So at the first one, the A stands for atomicity, so that all of the distinct actions appear to be a single atom, unbreakable whole. So the accumulation of all of the individual tasks and steps in the process seem like one. So the all succeed or the all fail notion exists, and if any of the operations in the transaction fail, the transaction fails. So we have an all or nothing type of consistency. We know that when we do an ATM, we do a withdrawal from an ATM, it's not just one task. There's several different tasks that occur in here. So when we make all those tasks seem like one task, we have to provide some facility to do this. When we do that, we create a transaction management object, and that object makes sure that these things actually happen. Consistency is what the C stands for in the ACID test, and consistency is that a transaction must transition data from one consistent state to another. So we have the current balance minus the withdrawal balance equals the ending balance. And we can take that ending balance and plus the withdrawal balance and still go back to the original balance, which is consistency. We actually have some applications out there that aren't very consistent. You know, they take stuff out. In fact, you see this all the time when you shop in a retail store. If you buy a bunch of stuff on a receipt and then start returning stuff, occasionally you'll notice, you know, the tax rate was returned incorrectly. Well, something was on sale, but when you bought it, it wasn't on sale, but it was on sale when you returned it, so they refunded you the sale price, you know, and then you start, you know, at the end of the day, the store's got to add all this stuff up, and then they go, oh, well, we're short by $200, or we're over $200, and it's because of inconsistencies in terms of the way the credits and the debits were done in terms of purchases and returns and all of the different transactions that are occurring throughout the day. Those inconsistencies are undesirable. So, I mean, as a customer, it's great if you bought it on sale, but you got the full price refunded to you. So, you know, you made money on that deal. Not so good for you in the opposite direction. However, the concept now throughout the years has transformed to the point where it doesn't really matter what the price is. It's whatever's on your receipt that's going to be matched up. So, you know, to ensure consistency in terms of the data integrity, they change the rules essentially to accommodate for and to create consistency. In fact, banks do this too. You know, tellers have to, at the end of the day, and you'd think it would be perfect, right? You know, at the end of the day, tellers never end up having a zero balance. You know, they're either over or under, like the drawer. In fact, if you work in sales, if anyone you have ever worked in retail sales, you know, especially, you know, as college students, it's a nice little job. At the end of the day, you're like, I'm $2 over, I'm $2 under. And you're trying to figure, where did this come from? How did that happen? Because you shorted somebody, or two bills stuck together, or something happened, you know, in terms of the consistency. So the I part of the acid test is isolation. Means that any changes made to data by a transaction are invisible to other concurrent transactions until the transaction commits, which means every time you go to the ATM machine and you stick your card in there and your PIN, you're isolated from the rest of the world. And hopefully what ends up happening is your account is locked, because you don't want to have two cards put in at the same time on the same account withdrawing the same amount of money. You know, what if you only have $20 in your checking account and you went and you have two ATM cards? So you and your friend go to two different ATM machines, simultaneously stick the cards in and enter your PIN, and you only have $20, but both of you are going to withdraw $20. So actually, believe it or not, in the old days that used to work. So it doesn't work anymore. Actually, nowadays you don't even get ATM cards with the same numbers on them anymore. Because if the cards, they used to print cards with the same numbers, and you went to two different machines, and you have an isolated transaction, which means the machine only knows about your transaction. It doesn't know about anything else that's going on simultaneously. If it's isolated, then you can withdraw $20, and then you can withdraw $20 over there, and over there, and over there, depending upon how many cards you have and your ability to log into the account. But now all the cards are kept separately, so the transactions can actually be merged together, and you can put a lock on the account that says one ATM has the account open and they're trying to do a withdrawal. Lock it so other accounts can't open it up, or other machines can't open up the same account and try to withdraw the same amount of money. So it requires that several concurrent transactions must produce the same results in the data as those of the same transactions executed serially. So simultaneous transactions or concurrent transactions don't actually occur concurrently. One of them occurs first, another one occurs second and third. So they're done in a serial fashion instead. So in reality, a system, whether it be an application server or a database itself, is going to be answering multiple different requests in parallel. So everything is going to be run. They should be able to be run in a serialized fashion, so it performs one at a time. And what ends up happening is you just queue up the applications so they all commit in a particular order, and so you can kind of tell what's going on. In fact, you see this in banking at at the end of the night, actually at midnight, when the bank reconciles. And what ends up happening is, you've got transactions that are occurring electronically, transactions that you're going to the bank and you're depositing. Let's say, for example, you get an electronic paycheck or something. And then during the day, you're making withdrawals. And what ends up happening at the end of the night, when all is said and done at the end of the day, everything has to be committed to the database in a serial kind of fashion. So usually what they'll end up doing is they'll take and do all of the all the credits first. So if you had any withdrawals, they come second. So it prevents, situations in which we have 5 transactions that are occurring. The user deposited their paycheck for $500, as an example. And then they spent all the $500. So if you process the payment first, the credits coming in, then you don't have any overdraft and you don't have any problems. You actually spent the money that you actually deposited in the same day. Versus the opposite scenario where the bank is going to end up and you're going to have very unhappy customers. Because if you deposit $500 and then you spend $500 throughout the day, which some people do actually, so then especially if you're traveling or something. Anyway, but long story short, if those deposits hit second and the withdrawals hit first, you're going to be negative, up positive, and then now you're zero. And then it causes banking issues. So the banks actually take this isolation and create a serial update that happens at midnight with a formula that says all of the credits come in first, all of the debits come in second. There's other rules to this too. And then at the end of the day, they can reconcile the account. And then after midnight, everything posts, and then the next day, things start out fresh again. And the transactions occur during the day. Transactions actually don't occur real time in any system, if you think about it. Because what you have is the possibility of there being mistakes. So if you are keeping track of each one of the daily transactions that occur, then if there's a mistake, and if you're committing everything in real time, there's a mistake, it's really hard to roll back. And it's really hard, and committing and rolling back is database terms. To commit means to save it to the database, to save it to the persistent storage. To roll it back means to pretend like the transaction never occurred and remove all of the different subparts of the tasks that were associated with that transaction so that we couldn't tell that the transaction ever was even attempted. So if we do this in real time and commit in real time, you end up with future errors, because you're going to have inconsistencies that occur if there's errors, if there's problems, and especially timing. The timing of the whole system might be totally off, which is why a lot of companies, including banks, do this reconciliation at midnight or at the end of the day. When customers aren't using it anymore, then when the traffic has slowed down a little bit, and then it goes through and analyzes all of the traffic for the entire day, and then it figures out what's going on, reconciles everything, and then you wake up in the morning and you go, my account's withdrawn. How'd that happen? It's because everything got committed and transmitted at night, essentially. And so the last part of the acid test is the D for durability, which is basically indicating that for durability, you're committing the changes and that they're permanent, and that failures that occur after a commit causes no loss of data. So implies that the data for all of the committed transactions can be recovered after a system or media failure as well. So durability just means it's going to outlast. So once the commit actually occurs, they're permanent. And there's not going to be any way that any other transaction is going to mess up the system. So we have transaction participants. So an application that uses transactions is called a transactional application. This is your vocabulary for today. And in the J2EE platform, the transaction application can consist of multiple servlets, JSP pages, and enterprise beans, which is a bunch of stuff I'm going to be talking about, probably not until next week, actually. The resource manager is the external system that's accessed by an application that keeps track of the transactions for us. Think of this sort of like the RMI environment that we have gone over already. So we are familiar with RMI at this point. In RMI, we had the registry, We told the registry that we had this object out there, and we gave the registry an interface, and we said, hey, look, these are the this is the template. This is what's available through this interface of all these objects. You can run these methods, and here's where the object's located. And the interface was sort of like the transaction manager. I said, well, okay, so I need to run this method. You go to the registry. And, oh, there it is over there. You find the object. You run the method on the object, which is kind of like what's happening behind the scenes. The same concept actually extends with servlets and JSP and Java Beans in terms of this type of environment. And we think about transaction management in this type of environment because everything is spread out all over the place. It's a distributed application, and which is what the servlet environment gives us, the distributed application. So when we have a distributed application, we have to worry about transaction management more so than if it was all on the same computer, you know, because we have more areas of potential faults in the code. We have you know, ability of something going down, a resource becoming unavailable, corrupted. So transaction management actually becomes a very important part of the system. The resource manager provides and enforces the ACID transaction properties for specific data and operations that exist. Examples of the resource manager include relational databases, which support persistent data and relational data, and EIS, Enterprise Information System, that manages transactional external functionality data, and the Java Messaging Service, JMS, which I'm going to talk about probably not until next week. The message provider manages transactional messages and the delivery of messages between components. So transactional application accesses a resource manager through what's called a transactional resource object. An example of this, we've seen an example of the transactional resource object, the connector object in JDBC. So we wrote a Java program several weeks ago, and we looked at the JDBC connection. And that JDBC connector object is the resource manager for the database. And so we create this object, and we tell the object to connect. And then we tell the object that we want to send an SQL statement. And the object gives us a result set, or it gives us something back, or it gives confirmation. Yes, command executed. That's a resource manager. It's managing the resource of the database, and our interface through this object allows us to access the database information. So we create these resource objects generally in the form of beans. So, well, what's a bean? Small Java program. So, following through the coffee reference, coffee beans, or beans themselves, are small, itsy-bitsy little Java programs that are generally created for special purpose applications. And one special purpose might be a bean that loads a connector driver for JDBC and connects to a database. So every one of our databases out there on the network that we're going to distribute all over and then connect through our application from our distributed application environment. Every time we want to use one of those databases, we're going to go to the bean. And we're going to ask the bean, you know, for a connection to that database, and the bean's going to say, okay, here's your connection, here's your result set, here's your information, and it's going to provide the resource management of that particular resource, which is how Java Beans actually fits into this kind of picture. We stick all the beans in a container, you know, and then we stick the container on the server, and then we go to the container and we look for the bean that we want. So it's very much a Java reference, actually, a coffee reference. You know, because for example, if you have a bunch of Java beans all over the place, unless you stick them in a jar, you stick them in a container, they're really hard to find them. They scatter out all over the floor, the table. So it's easier to manage them in a container. So we have container objects that hold beans, and we put the container objects in the servlet, and we load the container, and then we have container managers. So we have resource managers for containers, resource managers for resources that exist. So it's very much an abstract kind of concept. The resource adapter is the system library that makes the API of the resource manager available to the application server. A connector is a resource adapter that has an API conforming to the Java connector architecture. standard architecture for integrating J2EE applications and with EISs, Enterprise Information Systems. And well, that's why they call it the connector. The JDBC driver is really referred to as a connector object because it is providing the connection, or connector. But it doesn't necessarily mean something that is really in relationship only to databases. It could be a connector to a file server, to a multimedia application, to anything, actually. Here's another vocabulary word for you for today: transaction demarcation. And transactional programs must be able to start and end transactions and indicate whether or not the data changes are to be made permanent or whether they're going to be discarded. So indicating transaction boundaries of a program is called the transaction demarcation. So it's the indicator, it's the transaction boundary. So the transaction ends here, that's our demarcation that says we've completed the withdrawal and here's your money. At that point, you're going to mark it, and that's going to be the demarcation. It's going to say, this is the end of the transaction. And then usually you get in fact, you can tell in applications when this occurs because you can get a menu prompt that says, would you like to have your card returned or do you want to do another transaction? And sometimes, the application actually calls it a transaction. And they go, oh, okay, so transaction demarcation has occurred, and now we're ready to start a new transaction. So now that I've done a withdrawal, let's do a deposit. Or let's do something else. So the program starts the transaction by executing a begin. So the transaction manager object that you create would be a begin. You would perform a start or begin. The program then reads and modifies the scope of the new active transaction and performs all the different tasks. And then there's an end. So when the program is ready to make all the changes permanent, it executes what's called a commit operation, very similar and identical to what a commit means in terms of database terminology, and causes the transaction to be modified, and it creates, that is, or created during an active state, to actually be committed, to be saved. So successful completion of a committed operation results in permanent change of the transactional resource. So if a commit operation fails, for example, due to inadequate resources or data inconsistency violations or any problem, the resource manager executes a rollback and discards the changes. And the application may also explicitly request a rollback during an active transaction if a customer decides to quit. The customer decides, I changed my mind. I don't want to do a withdrawal anymore. So it's already halfway through the transaction. So if it hasn't saved anything yet, no problem. Just abort and then go back to where it was when it started. So these are distributed transactions that we're talking about, that I'm talking about, I guess. Distributed enterprise systems often need to access, update multiple transaction resources in order to accomplish some business goal. Multiple transaction resources would be an ATM machine going out to, because you're at a Citibank and you have Wells Fargo or something. It's going to go out. It's going to have to access your bank. It's going to have to go through a central system, a star network or something, to go and get to shared resources among different banks. So each one of those entry points for the distributed functionality would be considered part of the distributed transaction. And so you have to manage each one of those entry points and exit points from all of the different services or resources that are being accessed. So they're complex and more distributed transactions. We have issues that may be non-distributed because of latency, potential failures, one or more resource managers, or some interoperability concerns. Something is down, the network's down. I don't know, something went away, something's corrupted. So transactional application could itself handle rollbacks, commits, multiple distributed resources, but only at the cost of dealing with the complex situations and non-reusable logic. So if each one of the transactions on a local level dealt with it, you have a lot of repeat in functionality. As a particular example, if the ATM machine was doing all of the transaction management for all of the other components of the system, it would be bogged down and constantly checking, is the network still up? Yes, it is up. Okay, good. Did that work? Did you work? It's kind of like the manager who doesn't know how to delegate work and has to do everything himself or herself. because they haven't delegated it out to other objects or other people. And so they're constantly overworked, and they're really pretty much running slower than they would if they would just delegate some work out. So the same kind of parallel works with in terms of the distributed transactions. If one object is keeping track of the entire transaction and is doing all the transaction management, it's going to be like that overworked manager. So you separate it out among the different components, and you create transaction objects for each one of the different components and get them to self-manage. One of them reports back and says, hey, we had a problem, our network's down. Then the whole thing, globally can shut down. And there's no one component that's constantly checking. They're all individually responsible for their own work and for their own management. So, in terms of what the slide is telling you, multiple distributed resources, but only one, you can put it in multiple times, but you have the cost of, having to deal with complexity and the non-reusable logic per each one of them, or you can create a global system. So transactional applications themselves are good. The transactional content is the association of the transaction with the application component or the resource manager that is being used. So this would be the context of the transaction dealing with the component or the object. So the transparent forwarding of a transaction context from one component to another or from one component to a resource manager is another word down here, transaction context propagation. So this is forwarding the context from one component to another. The context is going to be the current transaction manager, the current transaction system that's being identified or being used. As an example, one object on the ATM machine goes over to the star network. You've got a transactional context propagation when the transactional control shifts from your local ATM to the star network. Now the context of the transaction is on the star network, and then the star network goes and connects to Wells Fargo or another bank. And then that context again propagated over to the other object and the other component. So you can call them components, you can call them objects. In any case, what you're dealing with is distributed components all taking care of their own transactions. And I've been kind of saying transaction manager a couple of times already, but this is the formal definition of what this actually entails. It's the common solution to the problem of coordinating distributed transactions to introduce a third participant. It's like the mediator. It's the transaction manager. Doesn't have anything to do with the functionality of the system. It's just out there watching. It's kind of like the micromanager who is out there watching the salespeople, making sure that the salespeople are doing their jobs correctly. And then if one salesperson isn't doing their job correctly, they get fired. And the transaction manager fires them, essentially. And then tells them, you need to start this transaction over again. Okay, take the customer's bill, reverse everything, and let's bring her up again correctly, kind of thing. So the transaction manager acts as the mediator between the application and the multiple resources of the application and what the application is actually using. So at any time during the distributed transaction, the transaction manager maintains an association between each one of the transactions, which has its own global ID, hopefully, some sort of an identification system, the application threads, and the connections to the resource managers. We can have more than one resource manager, as we've seen. Resource managers is like the connector that's going from the Java bean to the database. It's a resource manager for the database. We can have a resource manager for the file system, for the web server, for all the other different components. So here's our distributed transaction participants. And the slide's kind of fuzzy. I'm not quite sure why. Maybe because of the resolution. Transactional applications over here, and then we have our transaction demarcation. That's the stop point between all the different transactions. That works with the transaction manager. That says, okay, transaction manager, this is the beginning of the withdrawal. Now this is the end of the withdrawal. And did the withdrawal complete correctly? Yes, commit it. And then we have the resource accessor. To access resources, we go to the resource manager. Transaction manager also works with the resource manager. We say, is this resource available? Yes. And then let's open up a transaction. Okay. and then let me monitor all of the activity that's happening on the resource. If we have a resource manager, we have one central point that doesn't bog down the resource, which is kind of like why JDBC is actually kind of an interesting connector, because all of it goes through the JDBC connector, and if you set up a bean that does that, then you're minimizing the traffic that's going through the database, because it's all going through the connector object. A resource manager, and the resource manager can determine multiple transactions and duplicates and all sorts of different things, and not bother. It's kind of like the receptionist, not bother the database with all this traffic. The database only really gets the real calls that it needs to get. And the transaction manager that's supporting this, the receptionist at the beginning, at the front door, is filtering this traffic out to the correct resources. And not, otherwise, if everyone went over to the database and wanted to talk to the database directly, the database is going to be overwhelmed, so like getting help. So, locking and shadow pages. Sort of like how database implementations are done these days, actually. And I mentioned this before with the ATM example. If I go to an ATM machine, put my card in, access my account, I should hopefully have my account locked. And then if I go to another ATM machine and I access the same account, I should get what's called a shadow page. A shadow page, which is not a deep copy, but a shadow copy, which is the last saved version of what I had in my account before I locked it at the time of the lock, which means it's not updated. It's old data. And so you can restrict what happens on a shadow copy of that information. And you can, make sure, as an example, that the first transaction ends correctly before the second transaction on the shadow is allowed to commit. And if that one can't work, then the first one is rolled back, or the second one is failed. You roll it back, depending upon the situation. As an example, if I had $20 in the account, I went to ATM machine A and withdrew $20, and then I went to ATM machine B and tried to withdraw $20. One of them is going to pass, and one of them is going to fail. Probably the first one is going to work. The second one on the shadow copy is going to go, we updated after the save occurred on the first one. Now you have zero money in your account. Not going to work. So what does the slide say? The usual solution to simultaneously accessing to shared resources is to employ a locking device called a lock in a database, or a mutex in an operating system. It has a couple of different words used to describe the concept. Lock is probably more universally accepted. Mutex is only operating systems and Unix people like to use that word, but it's actually the same concept. It's a lock. It's an on or an off set on a access or a privilege. So a lock is a method of ensuring that only one process has exclusive privileges to change the state of the resource at one time. It's called mutual exclusion in a in a operating system environment. And it's called one resource at a time in a non-operating system perspective. Should multiple requests require access to the same resource, such as record, customer bank account, then only one is allowed to access the resource at a time. So you can't open up the same account and withdraw the same amount of money simultaneously 2 times in a row. Only one of them is going to work. So the ATM example used before, this is kind of a different one. When the verification of the account takes place, the lock is placed upon the particular row to ensure that it remains exactly as it is until the transaction is actually completed. And then at that time the customer account was to be deleted. It would either fail or have to wait for the ATM process that would have to acquire a lock until the customer's account was available. So it either has to unlock it and allow the access, or deny the access on an account. Let's say you've deleted the account, then you can't get to an account that's been deleted. So one process has the effect, or can have an effect on another process in terms of what's going on. So the wait would ensure that when the account is closed, the customer would receive only what is left in her account or his account, and not other things that don't belong. So, in terms of the basic locking concept, The basic problem that is the lock is required for both a reading and a writing to a particular resource in order to allow for consistency's sakes. So let's say, for example, you went in ATM number A and you withdrew $20 and you have a lock on there, and then ATM number B comes in and you want to open up the same account. Well, the last known balance in that account was $20. So if that shadow copy is delivered with a $20 balance, you've got inconsistencies. So what basically should happen is that the read should hopefully be updated from the last lock transaction so that the read is accurate. So number B, you come in and you say the read is 0 because you've withdrawn $20. So in a perfect world, that would be great. It doesn't always happen that way. It depends on the timing for when someone is actually accessing it, and then when the write actually occurs. So most people would design the transaction so that the writes occur before the reads, so that the data is consistent in the end. So if a second process were to read a row from the database while it was in use being modified, it might not receive an accurate value, essentially. So for lengthy transactions, any other process might have to wait until the read to read a single value. And that's such a good idea. So if you're constantly locking things and you have, well, in the form of an ATM transaction, you really are only supposed to use one ATM machine at a time. In other types of transactions, as an example, your ATM card that you were using by retailers, and that it would be impractical to continuously lock your card because it'll cause other transactions to fail or to be slowed down. Like you go to your bank and it said, "I'm sorry, your account is busy right now," all day. You're not going to be able to get anything done. You're not going to be able to do anything. So locking issues does not scale well. So with large numbers of transactions happening simultaneously, no, it doesn't scale well. So shadow pages, there's your definition of this new vocab word for you for today. The database makes a copy of the data that is undergoing the change. And one copy of the data is the pre-transaction copy, or the original value, and the other copy is undergoing the change. So all the read requests are forwarded to the pre-transaction copy that's ignorant of any changes that are underway. And should a second process decide to change, to make its change, then it will blocked by the locked on the data, and it will have to wait before it can actually make the change. Because it has a pre-transactional balance, it can't make the change. So you have to synchronize the writes, essentially, and allow things to happen in a serial fashion instead of a parallel or concurrent fashion. And here's kind of like the big picture of it all, if you can kind of see that. You've got writer number 1 and writer number 2 to a resource, and you have reader number 1 and reader number 2. And there's going to be a write request and then a read request, and then maybe the write is granted, and then another read request that's fulfilled before the write is granted. And what you're going to end up having is the concept here of when are the writes going to complete and when are the reads going to complete. And here you're reading it was fulfilled from a shadow, and the shadow was the old balance that was out here. So shadow copies are not up to date. Deep copies are up to date. A deep copy would wait until the first transaction committed, and then once the first transaction committed, then you're really getting a copy. You're going in deep. You're going in and you're getting the result of the first transaction as it's saved, and it's not a pre-transaction, it's a post-transaction balance that you're actually getting from a deep copy versus a shallow copy. Anyway, you can follow through the logic, but essentially what you're looking at are reads happening before writes, writes happening before reads, and then all of a sudden you have, oh, no consistencies, and then you have the shadow that checks. And if the shadow is wrong, you can't do it. As an example, if the shadow was of a $20 balance and ATM A withdrew $20 and ATM B withdrew the same $20, the B one's going to have a problem when it's working on that shadow copy because the shadow copy is wrong. It's out of sync. So when the shadow copy is updated, the transaction is not going to make any sense. B is going to fail. So we have this thing called a two-phase commit, and this actually sounds like a database terminology again. where we have resource managers that don't know about any others and can't cooperate directly with distributed transactions. Well, they don't know. They're all living on islands of their own in different object components. And so each transaction manager controls the transaction, indicating to each resource manager whether or when to commit or to roll back. And it's based on a global state of the transaction. So if you keep the global state into consideration, you can manage all of the smaller parts of the transaction. Transaction manager coordinates the transactions between the resource managers using what's called the two-phase commit protocol. And two-phase commit protocol provides the ACID properties of the transaction across multiple resources. What the two-phase is about is like it checks first and says, is this possible? Can we do it? And then the resources come back and I'll check out and I say, yes, you can. Then you do it. So there's just basically two steps to it. The first phase, the transaction manager tells the resource to prepare to commit, to perform all of the operations for a commit and be ready either to make the change permanent or to undo the changes. So it's kind of like putting a pre-lock on it. You know, say, hey, I've got this transaction that's going on and I just wanted to make you aware that the account is open and this transaction is going to happen. And then the resource manager over there says, okay, I'm waiting. And then it goes around all the other ones, unless it finds a problem with one of the other ones and says, well, you know, you can't do it right now. I'm sorry, I'm busy. I'm doing something else right now. I can't open up this account right here. This resource manager comes back and doesn't want to cooperate. Then you're not going to commit anything. All of them are going to be rolled back. And if all of the first phase are successful, then you're going to commit eventually. So each resource manager responds indicating whether or not the prepared operation was succeeded. You know, is this a good operation or is this not a good operation? Are we ready to do it or do we have to wait for something else? In the second phase, if all of the prepared operations succeed, the transaction manager tells the resource manager to commit their changes, make them permanent. Otherwise, it tells it to roll back and indicates a transaction failure to the application. So most transaction managers are using a two-phase commit protocol, especially in a distributed transaction environment, because you need to have coordination among multiple different resource managers. If you don't have that coordination, it's going to be practically impossible to kind of get everybody on the same page. It's like, okay, stop the world, stop all the transactions, everything. Okay, check to make sure, which you can't do. I mean, you can't just stop all the stuff that's happening in the application and check to see if something's going to work. So the Java 2 EE platform transactions, as I was mentioning before, it has the facility to, it has a Java JDA, Java transaction API that's used to control servlet components and distributed application components and resources to provide transaction management. So it supports a combination of servlets and JSP pages accessing multiple enterprise beans within a single transaction. I'm going to talk about enterprise beans probably not until next week, but the concept is that the transaction API is another object that is created, and that object, you have components that are, I don't want to use the word registered, but they're sort of registered with it. They're component aware, and they're watching, they're managing, not managing, they're just observing what's going on, and then you're just checking it. It's almost like a global state that it's creating for all of the local and remote objects that's going, all the behaviors that are happening and the transformations of all those different objects. So it supports both programmatic and declarative transaction demarcation. And the transaction management is a transaction component and application code that you're going to, that you write to go with it. And fortunately for you, you don't have to do that for this class. You don't have to actually write a transaction management system, and you probably wouldn't do it unless you're putting together a servlet environment and you're having multiple distributed components. Otherwise, there's no need for it really. So an application server implements necessary low-level transaction protocols, interactions between the transaction managers and resource managers, and distributed two-phase commit protocol. So requires only support for the so-called flat transactions, which cannot have nested transactions or child transactions inside of them. This would be like a transaction having a transaction inside of it. Can't do it. From a higher level transaction manager perspective, you're lucky if you can support the high-level transaction. If you go down deeper into sub-transactions that are nested inside, no way. Not without creating another transaction manager for each one of them. So here's an example of the transactions that cross multiple resource managers. So the following scenario illustrates the Java EE transaction that spans multiple resource managers. We have a client connects to a server. The server's got bean X, Y, and Z on it. Bean X, Y, and Z are providing connectivity. Let's call this one here, we know about this one, bean X already. He's a connector. He's connecting the JDBC component to the database. And then we have the resource down. These are the resources. So we have a message provider, an enterprise information system, and a database down here. And we're using beans as connectors to connect and to provide the resource management for each one of the resources down here. And the client is connecting to the resource managers. So this is a really good example of how you've got multiple resources that are all part of the same transaction. And so you create the transaction object to monitor and control all of the different resources. So then you have a perfect way of, well, semi-perfect way of controlling the transaction. So client X invokes a method on enterprise bean X. Client invokes a method on enterprise bean X. Bean X accesses database A using the JDBC connection. So we have bean X accessing the JDBC, using JDBC to access the database. Bean X accesses it using the JDBC connection. The enterprise bean X calls a method of another enterprise bean, maybe the one from Y, which sends a Java message, JMS message, to some other system using the message provider, which is here actually. So this guy here sends a message to here. So X is communicating with Y, Y is communicating with Z, the client's communicating with X. So this is all part of the same transaction environment. Enterprise bean Y then invokes a method on the enterprise bean Z, which updates and returns some data from an external EIS system, enterprise information system, using a resource adapter that implements a J2E connector architecture. And then the transaction manager in the J2E server coordinates the activities among all three of the different resources. So the transaction manager, the job of that object is to control communication and the transactions that are occurring between all of the different resources. And you're probably wondering, well, wouldn't it be easier to just make it into one? Then we can control it right there. And then you're not looking at a distributed application. You're looking at a client server. You're not distributing the behaviors or the abstraction at all. And we all know why you want to distribute it. Yeah, take advantage of computing power, resources, functionality. This might actually be owned by the same company, might be owned by different companies. It may not necessarily be, all the same application. It might be different components that are used with many different applications. I can think of this as working with the entire resources of the company in terms of the functionality. So the server ensures that the database updates of bean X and the message transmission of bean Y, and the EIS operations performed by bean Z either all commit or they all roll back. So the transaction manager is taking care of that. So now we have, and this was on one server, by the way. So this was the J2EE server, servlet common, and we're going to talk about servlets and servers next, probably next week. If we take the servers and we branch them out, we are working with the same concept. So the API works in both directions, with one server or with multiple servers. So in this case, the products can distribute transactions across multiple application servers. So we have bean X and bean Y and bean Z, same configuration as before, but we've branched them out onto different components now. So client invokes enterprise bean X, which updates the data on the enterprise system A. Here's enterprise system A, bean X, which then calls enterprise bean Y that is hosted on a different server. And then the enterprise bean Y performs a read-write access to enterprise bean system B, going this way. So bean X goes to bean Y talks to enterprise system B, A and B. And then when X invokes Y, the two servers coordinate, propagate the transaction between the contexts of X and Y. And this is where we're getting that transaction propagation and context propagation, and also demarcation that's occurring as well. Demarking the transaction that's occurring between all of this is identification of the transaction, and it's starting and end point. So transaction commit time, the two servers use the distributed two-phase protocol to ensure that the two enterprise information systems are updated within a single transaction. So they would need to use a two-phase commit approach, which is you're going to get that when you have distributed servers. If you don't have a distributed server, you may not necessarily need to use a two-phase commit because you don't have to check with different resources. It's all one resource. It knows or shouldn't know. You don't have to go out and query all of the different servers to see what's going on in the first phase. So here's the API that I've been talking about, the transaction technologies. The JTA, as it's abbreviated, stands for Java Transaction API, performs the specifications defined by the overall transactional behavior of the Java 2EE architecture. And the specifications define the contract between the application servers, resource managers, and transaction managers. You're never going to create an instance of this object unless you're dealing with transaction management. It's not really part of the regular development. And usually you have somebody who's keeping track of the architecture of the system, and they're performing the transaction management. So it defines the requirements, the management runtime environment that exists. Specifies standard Java interfaces between a transaction manager and a distributed transaction participants that it's coordinating with. Applications, application servers, resource managers, all of the different pieces of the puzzle. And JTA defines the interfaces that lets the application servers, resources participate regardless of their implementations. Well, it's all written in Java, so it's all in Java compatible communication protocols. However, some of the Java beans might be running JDBC, some of them might be running RMI, some of them might be running other servlet technologies. And in that case, they are sort of different resources, but they're all the same in terms of how they're controlled by the transaction manager, or transaction API, I should say. So the JTA transaction is a transaction managed and coordinated by the J2EE platform. So we talk about it as a JTA transaction, and it can span multiple components in enterprise information systems, and the transaction is propagated automatically between the components and the information systems themselves. Here's an example on the bottom. For example, a JTA transaction may comprise a servlet or a JSP page accessing multiple enterprise beans, some of which access one or more resource managers or other components in the system. So you can mix and match Java components. And the transactions themselves begin with an explicitly in the code or implicitly by the enterprise Java Bean server. So we have this enterprise Java Bean server that manages the container for the beans that are acting as the resource managers. So it's kind of a nested hierarchy of functionality. But the server itself, and this would be an EJB. These are EJBs, Enterprise Java Bean servers, because they're servers holding Java Beans. The Java Beans are connecting to servlets, are connecting to resources like databases and applications and things. So a component can explicitly begin the transaction using the Java X transaction. This is the import that you're using on the classes. The main benefit of the transaction is this ability to combine multiple components, enterprise information system accesses into one single transaction with very little programming effort, and propagates transactions between multiple components, enterprise systems with no additional programming efforts at all. So the same effort to connect 2 servers is used to connect 10 servers. So there's no additional effort and there's no additional configuration to it. We have client tier transactions and server tiered transactions. So client tier does not require transaction support What's a client tier? Well, it would be applets. JSP is actually a server tier technology. Applets, JavaScript, which is not really even part of Java. Anything happening on the client, no transaction support. It's all done on the server. Like the distributed transactions, the products themselves might choose to provide its capability for added value, but it's not really part of the configuration. To ensure portability, applets and application clients should delegate transactional work to enterprise beans, either directly or by way of a web tier. So usually you have a web tier that connects to the enterprise Java Bean server, and the Java Bean server is going to essentially serve up the application to the web tier, and the web tier is going to deliver it to the client. The client's interface, we don't care about the transactions occurring on the client. Nothing's occurring on the client. However, in the old days, not happening very much anymore, but applets were used for some of the functionality, and the applet is sort of like the front-end user interface, because you can connect an applet to the back-end server and consider that part of the transaction, which is what the slide is alluding to, but not so much used anymore. Web tier transaction guidelines. So the web tier is the front end. It's the HTTP portal into the server. It's usually housed on a single computer, but it may also be containing the enterprise Java Bean servers, and it might actually be all on one physical machine, or it might be separated out. But the tier itself, the servlets and the JSP pages in a two-tiered application can access enterprise information systems within the scope of the transaction, the Java transaction API transaction. So servlets and JSP pages support only programmatic transaction demarcation, which means inside of the program you are telling the bean to you're checking with the transaction object, and you're registering things and events that are occurring with the object through the web server. A servlet or a JSP page that uses the lookup service, JNDI, to look up the user transaction object using standard naming convention. Defined name is going to be using this particular API component, and then it uses a user transaction interface for the demarked transactions. So it's kind of like we had an RMI interface to objects that gave us our public methods that were available. Well, the user transaction interface object tells us which pieces of the functionality are part of the transaction, and it creates our transaction demarcation so that the transaction object can check the interface and go, well, this occurred, that failed. Oh, fail. Roll back the transaction. So it basically configures the transaction for the transaction manager object that's created. Here's an example illustrating the use of the JTA user transaction interface to demark transactions with a servlet. And don't have very much code here, but do have an instance of a context that's created, initial context of the transaction, and then we're going to create a user transaction object UT that's going to look up the information for the context and find the object or find the information of the task that's actually going to be done. Oh, the code is missing in here though. Begin it, access the resources transactionally, and then end it essentially. So the user, the .begin associates the calling thread with the new transaction context, and say the context could be this is a withdrawal, this is a deposit, or this is a balance check. And then you go through and you, well, what's part of a withdrawal? What's part of a balance check? And then you process the transactional statements that are associated with it, and then you end it, and then you can do a check on that from the context of the transaction to see if you should save it or not save it. So accessing subsequent accesses of transactional resources such as JDBC connections, resource connectors, they're implicitly enlisted through the resources in terms of, or into the transaction. So they're all part of the same system. They're incorporated automatically through the instructions that are included in between the begin and the commit. The commit itself saves the transaction and uses a two-phase protocol if necessary. And that would be programmed in, actually. So enterprise Java Bean tier transactions. So the enterprise bean itself offers two types of transaction demarcation. We have bean managed and container managed. So as remember before I said beans are small little pieces of coffee. They're beans, small little programs. And it's very likely to put those small little programs inside of a container. So putting the beans in a jar, coffee can. And you can do the management on the can or the jar, or you can do it on each one of the individual beans. It's easier to do it on the container because then you can control all of the beans with one or two checks on the transaction. However, it doesn't give you as much flexibility as if you control them, micromanage each one of those beans that's inside of that container. So that's the pros and cons to it. The container managed transaction demarcation, there's 6 different transaction attributes associated with it. And we've got, this is required. This requires new. This is not supported. Support's mandatory. Never. All sorts of different attributes that we can put on different pieces in terms of the transaction. The application component provider or assembler specifies the type of transaction demarcation, the transaction attributes for each one of the methods of the enterprise bean in the deployment descriptor. Deployment descriptor is an XML file. Did we go over that yet in this class? Probably not until we get to servlets, because we haven't looked at beans yet, so we haven't looked at deployment descriptors. But they're XML file interfaces that describe the makeup of the bean component for the application. We'll get into that. It's nothing more than information about the information about the functionality. It's an XML interface. So bean managed transaction demarcation. So what we looked at before, the first part of it was container managed, where we had 6 different transactional attributes. In the bean managed, the enterprise bean uses the JavaX transaction.user transaction interface to explicitly demark transaction boundaries. And then we have a couple of different types of beans. So beans come in 2 different forms. We have session beans and entity beans in terms of servlet technologies. And don't worry if you don't understand any of the bean stuff yet, because we're going to get that next week. I'm going to save beans for a separate lecture in itself. But to finish out and this is the last part actually of the transaction management part of the beans. And I'll hit transaction management a little bit more as we start talking about the different types of beans as well next week. The session beans and message-driven beans can choose to use bean managed demarcation. Entity beans must always use container managed demarcation, transaction demarcation. So bean managed transactions. The following pseudocode illustrates a kind of fine-grained control to obtain bean managed transactions. So by checking various different conditions in the pseudocode, you decide whether to start or stop various different transactions within the business method or the logic that's occurring. What you're doing is you're putting on each one of the checks, you updated a table, you edited a table, you ran something, you executed an algorithm, you made a calculation. It's from the bean managed transaction is from a source code perspective in terms of the implementation of the functionality of that bean, and you're putting the checks in as you're writing through the fine detail of the algorithm and the fine detail of the information you're programming into the bean functionality. So we have an enterprise bean using the JTA transaction. Same syntax as before. We're creating a user transaction object. We're saying begin the object, perform the transactional work, and then commit the object. So the interface is used in the same way as the enterprise Java Bean tier. To reference the interface, it's obtained by calling the context.getUserTransaction instead of the naming lookup, because we don't have to go in between server components. This is all contained inside of the same component. So we don't have to use the Java naming lookup for it. Instead, we can just ask it to get the context, get user context of the bean, the information inside of the beans. In terms of the container managed transaction demarcation, and it is like a tongue twister by the time I end with this lecture. Let's see, the boundaries for the enterprise beans that use container-managed transaction demarcation is what we're talking about. So it's the boundaries from the container perspective. The transaction attributes for an enterprise bean method determines the method's transactional semantics. Defining the behavior of the enterprise Java bean container must provide when the method is actually called. And then transaction attributes are associated with the enterprise bean methods in the bean's deployment descriptor. Very similar, except for you're doing it in the container level instead of the bean level, which is the same. It's the same essential concept of the transaction demarcation. It just depends on where and how you're defining it. And you're using the bean's deployment descriptor, the XML interface to that bean, that's basically providing the interface to the bean. You're using that to get the attributes that are associated with the transaction. So for example, if a method has a transaction attribute that says requires new, the enterprise Java bean container begins a new transaction, JTA transaction, every time the method is called and attempts to commit the transaction before the method returns, because it requires a new one. So as an attribute, it creates a new object for the a new transaction object. The same transaction attribute can be specified for all of the different methods in the enterprise beans, or different attributes can be specified for each one of the methods of a bean in the container. So you can do an all or nothing on the methods that are in the particular beans that are in the container. So although it's on a container level, you don't have to apply it towards all the beans. Just be a certain subset. Even in container managed demarcation, an enterprise bean has some control over the transaction as well. You can use bean controlled, bean managed, as well as container managed simultaneously. So for example, an enterprise bean can choose to roll back a transaction started by the container using the methods set rollback only on session contexts, entity contexts, and managed driven contexts, objects that are bean driven instead of container driven, depending upon the implementation. Benefits of using container managed transaction demarcation. The transaction behavior of an enterprise bean is specifically or specified declaratively instead of programmatically. Yeah. All right. On a container, you're controlling it from the outside in. You're not controlling it from the source code. On the beans themselves, you're writing it in the source code. So it's easier to change something that's not ingrained in the bean, that's not part of the bean implementation, that's not done programmatically. It's better to do it, it's easier to do it on a container level, because then you're managing something outside of those objects. So it's more flexible. It's a separate component object. It is less error prone because the container handles transaction demarcation automatically. Well, we have container control, so we can have control from a container perspective. It's easier to compose multiple enterprise beans to perform certain tasks with specific transaction behavior, to get multiple beans to work together for certain tasks. And the application assembler that understands the application can customize the transaction attributes in the deployment descriptor without any code modifications. If you do it at a bean managed level, you have to modify all the code and all the beans that you're managing separately to do this with. And you're probably wondering at this point, well, lots of flexibility, yes. When am I ever going to use this? Interesting. If you put together a bean server, enterprise Java bean, and a server, and you've got tons of beans and they're all in a container, and it's like management of the management. It's taking and you're providing transaction control for a lot of small little pieces and components, and it's almost like writing a program to manage the program. In theory is what you're doing actually. So you're designing a program to manage the program, and the program that you're designing is the transaction manager. And the transaction manager is controlling the beans at a container level, and some of the beans are probably going to be managed at a bean level depending upon the bean, the functionality of what that bean is used for. And you're also keeping track of the multiple servers and the resources that the servers are actually using. Transaction attributes. So it's the value associated with a method of an enterprise bean that uses a container managed transaction demarcation. Is the attribute in terms of the transaction attribute definition. And the transaction attribute is defined for the enterprise bean method for the bean's deployment descriptor. It's the little XML file interface for the bean. usually by an application component provider or an application assembler. And the transaction attribute controls how the enterprise Java bean container demarcates transactions of the enterprise bean methods. So depends on what method behavior is all being controlled by the attributes. Hopefully, or being tracked by the attributes, I should say. In most cases, all methods of an enterprise bean will have the same transaction attributes, which definitely would make things a little bit simpler. Otherwise, you can have millions and millions and millions of attributes associated with all of the different methods of all the different beans that are inside of a container, which can be a little bit overwhelming. So what are some of these attribute settings? And I'm just going to kind of give you a brief overview of what these, and there's 6 of them total. The required new. These are the kind of things we've seen in some of the examples I've shown you. But just to give you the formal definition of it, if it's required, you're using as the default transaction attribute to ensure that the methods are invoked. Causes the enterprise bean to use existing transactional contacts if it exists, or create one. If it does not exist, it means it's required. You actually have to have it. The attribute has to be set. Required new uses the results of the method must be committed regardless of whether or not the caller's transaction succeeds. So the results, whether it's a failure or a success, is recorded. For, let's say, for example, logging situations, for how many attempts something was made, actually logging is a good example, but how many attempts something was made, how many failures, what kind of error messages occurred, would be a good example of a required new kind of functionality. Supports used for methods that either do not change the database or update automatically, and it does not matter if the updates occur in a transaction. Mandatory is used when the method absolutely requires an existing transaction. Mandatory. Never is used to ensure that transaction client does not access methods that are not capable of participating in the transaction. So it will never access that particular method. Not supported is used when the enterprise bean accesses a resource manager that neither does not support the external transaction demarcation or does not support Java 2 EE is written in a different language or a different technology, so it's not supported. So, if you remember the university register example I gave you for the RMI, ask the register example about going back and forth. There's another one. I don't believe I have it on the behacker.com website because it failed to work successfully. So it had a few problems, and then I decided it's not worth it. And you guys don't have to do this for any of your programming assignments, so I decided the example itself I'll just skip. Instead, you can see the source code here in this slide for a session bean example of what the university register program would produce. If you remember the theme, it was just a client server where one client was asking the university program, ask the register if a class was available. It would come back and say, yeah, you're registered. No, you're not registered. So this one, you're seeing inside of the source code where it says, get university name is this method up here. And inside the method, we've got a transaction object that's created from user transaction. If you were to program this is sort of what it would look like. It's a session context, so it's done for a session bean. And you have a transaction.begin, and then you have a transaction.commit showing you. It's actually, the programming part of it is not quite as convoluted as the concepts behind it. It's pretty easy actually. You create the object, you put the object inside of the method. You begin the recording of the transaction. You put some lines of code in there to have something happen. You end it. And then the transaction manager object keeps track, almost like a log, of all of the status indication of what occurred. And then if it's successful, after you've done a try here and everything worked out successfully, you didn't get any error message, nothing came back out of it, it commits it. So it's kind of a way of putting a check in on top of the code from a bean. This is bean managed, by the way, or session bean managed, I should say, where you're putting it in programmatically inside of the code. You're creating the object and you're starting it up and you're ending it, and you're performing the transaction management from method by method in terms of the functionality. I usually, at this point, kind of equate this to unit testing. If you've ever written JUnit tests, you know that you have to write for as many classes with as many methods that you create in Java, you have to create a corresponding test that associates with it. And it's almost twice as much work to write the test cases than it is to actually write the source code initially. Transaction management is a same kind of concept. You actually have to put it in here as a separate program that's running with the program. That is almost as much work as writing the program. But the thing is, the benefit of testing, especially with JUnit, is that you actually can test the functionality of the method, all the ins, all the outs, all the produced results, and all the failures. Well, if you put the transaction management in here, then you're testing. And you're not testing, but you're ensuring that the transaction is completing successfully. And you're able to track the status of all of the different points in the context of the transaction. And you're able to establish the transaction demarcation, and you're able to actually establish whether or not all of these components worked correctly in terms of their communication. So that, believe it or not, is all I'm going to give you on the Java Transaction API. This link still works. You can actually, let me just make sure you click on the link here, and you can see it'll take you to the Java Sun Products JTA website, and the JTA website will go through all the specifics for the Java interface between the transaction manager and all of the different parties that are involved associated with the implementation in the distributed transaction system. You're going to possibly run into this further down the road in a real client, real working situation, or you'll never see this at all in your entire career. Depends on what area you're working in. If you're doing system administration and you're working at a programming level, you're configuring servers, you're configuring containers, you're working with session beans, you're working with servlets, you're probably going to run into transaction management. And it's going to be probably done on a basic level. It's not going to be done like, being managed, container managed. You're not going to have all of the different pieces of it probably employed, just certain things to keep certain checks. It's kind of like testing. Not everyone does complete testing of everything. And there are so many different methods and so many different ways of testing an application. Nobody does 100% coverage of the entire program, nor do they actually implement all of those different techniques. In a perfect world, when time and resources are unlimited, yeah, you would do it all. However, not very practical. So you'll get transaction management sort of with the same sort of philosophy. It'll either be done in a little bit here and there, or it'll be skipped completely, or it'll be part of the UI or something, or you'll be doing it to an extreme because it's a banking application and you don't want your ATM application to fail or something of that nature. So anyway, so that's my spiel on the Transaction API. Everything you ever wanted to know about transaction management. Hopefully it wasn't too much for you. A lot of vocabulary. And you'll be happy to know that you don't have to write any programs for this class with it, but it is one of the topics I needed to cover. So next time we're going to be looking at Java JSP. We're going to be looking at web tiers and JSP and the differences between the container objects and how the objects work with JSP and how servlets work. And all that stuff is for the topic next week. That is going to be all for this week. Thank you for showing up.